For decades, the invisible threads of rare earth metal dominance have held the world's most advanced technologies captive. Over years of strategic investments, lax environmental regulations, and low labor costs, China has secured a near monopoly on rare earth metal mining and especially processing, commanding the global supply chain. Early on, they recognized the critical role of rare earths in high-tech industries, ranging from electric vehicle batteries and motors to wind turbines, smartphones, and military technologies. China leveraged rare earths to bolster its economic and geopolitical influence. Nations watched anxiously, industries teetered on the edge of stagnation, all because a handful of elements dictated the future, which was now largely directed by China's authority. But while others feared the tightening grip, Tesla took matters into their own hands and attempted to achieve the impossible. What began as an obsessive quest for ultimate efficiency and a relentless drive to shatter manufacturing costs quietly became an unexpected masterstroke. When China recently attempted to flex its rare earth leverage, expecting widespread disruption, Tesla didn't budge. Instead, they just pulled back the curtain on their game-changing new motor, engineered from the ground up, completely free of rare earth metals. And this isn't some lab experiment, it's now at the core of Tesla's entire fleet, ripping up the old playbook and shifting the power dynamic forever. Before we continue, stop using Yahoo Finance, stop using Google Finance, and visit my newly redesigned website, themarketisopen.com, for instant stock quotes and quarterly financial data going back up to 17 years, and it's all freely available. Electric vehicles are at the forefront of the global energy transition, fundamentally relying on high-performance electric motors for propulsion. Permanent magnet motors have emerged as the dominant choice in the EV market, capturing over 80% of the market share, and this is primarily due to their superior efficiency and high power density. However, these motors extensively utilize rare earth elements such as neodymium, dysprosium, and terbium, which are crucial for providing the necessary magnetic strength required for the operation of EVs. But this introduces a complex array of challenges that extend beyond their favorable chemical properties and technical specifications. Tesla is caught in the middle of a heated trade war between the US and China. Just recently, in early 2025, China imposed a ban on shipping its rare earth metals to the United States. The global supply chain for rare earths is heavily concentrated in China, as the country controls over 85 to 90% of the world's rare earth elements refining capacity and more than 90% of the production of rare earth permanent magnets. This creates significant geopolitical risks and supply chain vulnerabilities, as evidenced by China's historical use of export restrictions as a political tool. And this vulnerability was recently underscored by Elon Musk during Tesla's Q1 2025 earnings call, where he revealed that China's export restrictions on rare earth magnets implemented in April 2025 directly impacted the production of Tesla's Optimus humanoid robots. Tesla required special clearance in order to import these materials and prove that they wouldn't be used in military applications. But shockingly, Elon Musk barely even blinked when it came to the rest of Tesla, which was supposed to rely heavily on rare earths. He announced on the conference call that Tesla as a whole does not need to use permanent magnets. This is a stunning revelation, as Tesla appears to have sidestepped what would normally be a devastating impact to its business, but instead they shrugged it off. Tesla started decoupling itself away from China, a journey that began years earlier as outlined during Tesla's 2023 Investor Day, and Tesla is just starting to reap the rewards now. Tesla recognized the potential geopolitical risk of depending solely on China in the long term for its high-volume electric motors. They proactively took steps to reduce its exposure and thereby enhance long-term production stability. But a major factor in this decision was the substantial impact of rare earth mining and refining. Rare earth extraction and refining is energy-intensive and environmentally harmful, producing significant toxic waste and radioactive residue. For example, 1 ton of rare earth elements can generate about 2,000 tons of toxic waste and 1 ton of radioactive residue, plus dust, waste gas, and waste water. These practices cause long-term ecological damage, with polluted regions in China needing decades to recover. Furthermore, extracting rare earths is an expensive endeavor and contributes significantly to the overall production cost of electric vehicles. With demand for these materials expected to increase 400 to 600% over the next few decades, means that the current reliance on these elements is deemed unsustainable for the long-term growth of the EV industry. As stated by Colin Campbell, VP of Powertrain Engineering at Tesla in 2023, as the world transitions to clean energy, demand for rare earths is really increasing dramatically. And not only is it going to be a little hard to meet that demand by mining that rare earth, it has environmental and health risks. And that's why Tesla made the strategic decision to focus on reducing and removing rare earths from its supply chain. To fully appreciate Tesla's pivot, it's important to understand the fundamental differences between the magnet technologies involved. Neodymium iron boron magnets currently being used in EV motors offer exceptional strength, high coercivity, which is resistance to demagnetization, and high remanence, meaning that they can maintain a strong magnetic field even without an external magnetizing force, generating 1.4 Tesla fields, a unit of measurement, not the company, but keep this number in mind, making them ideal for compact, high-torque electric vehicle motors. However, their high cost, price volatility, and China-dominated supply chain pose economic and geopolitical risks. Extraction causes relatively severe environmental damage, including toxic and radioactive waste. These magnets also have lower, what's called the Curie temperature, and can demagnetize at high temperatures starting at 310 degrees Celsius, challenging their use in automotive applications. Ferrite magnets, on the other hand, which seem to be what Tesla has selected for their next generation motors, are ferromagnetic metal oxides, or a type of ceramic, and are cheaper and more abundant than rare earth magnets, offering a stable supply chain and higher Curie temperature for better thermal stability up to 450 degrees Celsius. And they have proven uses today, such as in applications like loudspeakers. However, their weaker magnetic field, 0.5 to 1 Tesla, versus neodymium iron boron's 1.4 Tesla, requires more material, resulting in heavier, bulkier motors that may reduce vehicle range unless offset by other design efficiencies. There is also up-and-coming alternatives being researched, including iron nitride magnets made from abundant iron and nitrogen, which offer a low-cost, rare earth-free alternative with high coercivity and a potential for mass production at less than half the cost of rare earth magnets. They may achieve up to 3 times the energy density of neodymium magnets with a higher Curie temperature and 2.4 Tesla flux density, ideal for EV motors. Despite past manufacturing challenges, companies like Niron Magnetics claim to have resolved these, though large-scale automotive use seems to be still developing, and it's not clear if Tesla has gone this route. Now, Tesla still requires rare earths in low volumes for its Optimus robot, which Elon Musk did seem devastated about on the conference call, as China was essentially hampering the production of these robots, which aren't even consumer products yet. But Elon Musk is obviously adamant on accelerating robot production, for reasons we highlighted in our previous video. Optimus still needs rare earth magnets in its motors and actuators, as they provide high power density and the ability to miniaturize parts, especially while Tesla is still developing prototypes for this robot. When Optimus enters truly mass production, it's likely that Tesla will consider ways to reduce rare earths in this area as well. For vehicles, Tesla's next generation powertrain, designed to be rare earth free, targets an insane $1,000 cost through the integration of various innovations in their motor and battery technology. Plus, this will likely be applied to the mass-produced Cybercab, which will have a smaller battery pack and other manufacturing advances like the unbox process, single-unit castings, and 48-volt and 800-volt architectures, all coming together to make the vehicle as cheap as possible to manufacture. But to overcome the lower magnetic flux density of ferrite magnets, Tesla already uses and may be exploring new techniques, including advanced rotor designs and novel motor architectures, utilizing tools such as spoke-type IPM, Hall-back arrays, and axial flux motors. Spoke-type IPM, or internal permanent magnet rotors, arrange ferrite magnets in a radial spoke-like pattern inside the rotor to boost performance. This design focuses magnetic flux towards the stator, increasing the torque and air gap flux density despite ferrite's weaker magnetism, 0.4 teslas versus 1.4 for neodymium. It also adds reluctance torque for extra power, achieving near 98% efficiency. However, according to Model 3 studies, high-speed performance in the field-weakening region needs further optimization. Hall-back arrays align magnets to create a strong magnetic field on one side towards the stator, while canceling it out on the other, amplifying flux density. This allows ferrite magnets to deliver higher torque and power in a compact design, reducing material waste. While promising, as shown in a Model 3 study with a 10-degree step array, they struggle at high speeds and require complex manufacturing, making them a high-skill, high-reward solution. And axial motors, or pancake motors, use a disc-shaped design with flux flowing parallel to the motor's axis, ideal for in-wheel EV setups. They offer high power density and efficiency, 95 to 98%, by maximizing magnetic surface area and minimizing energy losses. Segmented stators and pole slot combos optimize ferrite performance, but their complex design demands precise engineering to compete with traditional motors. Tesla already employs similar technologies in their current permanent magnet motors. For instance, Tesla's rare earth-free motor follows a motor that already had a 25% reduction in rare earth usage in Model 3 and Y powertrains from 2017 to 2022, reflecting years of iterative engineering. But one of the highlights from Tesla's Investor Day was their strength in building their own custom tools and software, which they say are the best in the world. Using modern optimization algorithms and simulation technologies, engineers can model and refine motor dimensions, field weakening capabilities, and predict performance across various operating conditions, enabling the achievement of design objectives previously deemed unattainable. Tesla says that getting the simulation exactly right is central to the cost, the weight, the size, and even the sound of the drive unit. So they can switch out the type of magnets and then analyze through software the new placements and architecture changes needed to optimize the new motor. Now, despite the material differences, studies suggest that ferrite-based motors can achieve nearly the same peak efficiency, around 98%, as rare earth permanent magnet motors. The challenge lies in maintaining this efficiency across a wide range of speeds and loads without sacrificing power. Tesla stated during Investor Day that their rare earth-free motor would actually end up being cheaper and more efficient than their permanent magnet motor, making it a no-brainer to make the switch. And that seems to be exactly what they've done. While there are still many details to be released, it appears that Tesla has indeed made a breakthrough in rare earth metal-free motors and has implemented this change throughout their fleet, as evidenced by Elon Musk announcing that Tesla as a whole no longer relies on rare earth metals. The new ferrite motor that Tesla is working on is not entirely novel, but rather a sophisticated re-engineering and reapplication of existing, more abundant material technologies, primarily advanced ferrite magnets and potentially emerging iron nitride magnets. This approach is enabled by cutting-edge computational design, novel motor topologies such as axial flux, spoke type, and Hall-back arrays, and revolutionary manufacturing processes to mass produce this at scale. The implications of Tesla's pioneering effort extend far beyond the company itself. By publicly committing to and demonstrating the feasibility of rare earth-free permanent magnet motors, Tesla is setting a new, more sustainable benchmark for the entire EV industry, all while insulating itself from geopolitical tensions between the United States and China. So do you think Tesla has already achieved and rolled out these breakthroughs in motor design at scale? And what other challenges pose a risk for Tesla's complex global supply chain? Don't forget to watch my last video on Tesla's new learning techniques for the Optimus humanoid robot. Visit our new website, themarketisopen.com. Please hit the like button and subscribe. We would really appreciate that. And a huge shout out to all of our patrons that help to support our channel. Your support helps us to continue to make great content. Thank you guys so much for watching.